Look at this ruler. Between 0 and 1 centimeter, there is a gap. Between 0 and 100 centimeter, there is much larger gap. If I asked you, which of these distances contains more points, you would probably think, I'm asking a trick question. Obviously, the 100 centimeter line is bigger, so it must have more points. Right? Our brains are evolved to understand finite things, like a bucket of water, miles of road, or 1,000 subscribers. But in the world of mathematics, your intuition is lying to you. Today, I'm going to prove you that a 1 millimeter silver of thread contains the exact same number of points as a line stretching across the entire observable universe. Let's start with the basic. What is a point? In geometry, a point has no width, no height, and no depth. It has zero size. If you have a 2 centimeter line, how many of these zero size points can you fit in? Well, if you pick any 2 points, no matter how close they are, you can always find a third point right in the middle, and then another between those two. This is called the density property. Because you can do this forever, every line segment contains an infinite number of points. But here is where it gets weird. People assume that because 3 cm is longer than 2 cm, it must be a bigger infinity. But in maths, we don't just guess, we pair up. If two sets are equal, then we should be able to pair them up. To see if two sets are the same size, mathematics use something called bijection or one-to-one correspondence. Think of it like a dance. If every person has exactly one partner and nobody is left standing alone, then the number of people in the both groups must be equal. If we project light from a single point of this line, every single point on the 2 cm line maps to exactly one unique point on the 3 cm line. There isn't any single point on the shorter line that doesn't have a partner on longer line, and crucially, there isn't a single point on the longer line that is left lonely. We have paired them perfectly. This proves they have the same cardinality. In eyes of infinity, these two lines are identical in population, even though one is physically longer. Now you might be thinking, okay, so all infinities are the same? But that's the second trap. In late 1800s, Georg Cantor discovered that some infinities are actually bigger than others. He showed that infinity of the counting numbers 1, 2, 3, 4 and so on is the smallest kind of infinity. We call this aleph-null or countable infinities. But the number of points in our 2 cm line that is different beast entirely is called the cardinality of continuum. Cantor proved that you cannot pair the points on a line with the whole numbers. There are so many points on that 2 cm line that they overwhelm the infinity of the whole numbers. This feels like a paradox because we confuse measure with cardinality. Measure is about space. 3 cm is objectively more space than 2 cm, but cardinality is about the number of elements. When you deal with infinity, the rules of addition, subtraction that we learned in the kindergarten breaks down. It means that within every tiny flick of your finger, there is a vastness that is just as big as space between the stars. We live our life in the finite, but we are surrounded and even composed of infinite complexities. I am Curious Toad. Thank you for watching this video.